Okay, wonderful. Welcome. Thank you all for being here. My name is Karthik Ramanathan, and I am brand new faculty out here at WashU. I just moved to St. Louis maybe about 3.5 to 4 months ago. So I'm starting to get my lab set up over here. I'm a new physics professor in the department. And I figured it'd be a wonderful opportunity to talk about my research to the wider audience and maybe tell people about some of the exciting work that we'll be doing in my lab and in the future. So my talk is going to be about the field I work in, which is understanding the nature of dark matter using terrestrial experiments, which is a pretty opaque phrase, right? It's a mouthful. What exactly do you mean dark matter? What exactly do you mean you're experimenting? It's all concepts we'll cover. But then what I want to get across is that these are leading questions at the forefront of astrophysics research, and we're going to be talking about things that we don't completely understand at all. The other thing I want to say about this lecture is that this is going to be a little bit of a meandering journey. We'll touch on the actual science and the modern science near the end of the talk, but then the first bit will be a little bit of a preamble setting up the scene of what exactly this dark matter is, what the problem in modern astronomy and astrophysics is. So are we all on board with that? Wonderful. Okay, so this is not going to be a particularly interactive talk, I'm going to say, but I do want to ask one question to the wider audience. If I asked you to go out tonight and stare up at the sky, what might you see?
The moon.
The moon, right? What else might you see? Planets, stars, exactly. I would have also accepted nothing, right? Because we live in cities, right, with a lot of light pollution and stuff like that. So you may go up to the night sky and you may stare up and you'll see a scene that looks like this, flooded with light from all sorts of buildings, and you may be able to pick out 1 or 2 stars over there, depending on where you are, or depending on how far out you go. So I've moved to Creve Coeur, and then if I keep driving even further west, eventually I can start to see a little bit more than that. So this has not always been the case, right? Our ancestors, when they looked up at the sky, right, we're talking about the humans who evolved 300,000 years ago, and even before that, all the hominins that existed, all the way up to about maybe 1880, right? If you looked up at the sky, what did you see? You saw wonderful things. You saw thousands and thousands of stars. You saw these interesting features like the streaks of color. You maybe saw a few shooting stars here and there. And this was regardless of where you went to outside, basically. And until industry happened, this is the sky you saw. But also interesting here, right, is this idea of that's a little bit paradoxical. You saw so much motion in the night sky. You saw all these stars moving, all the shooting stars and stuff like that. But you also had the sense of repeatability. You knew that maybe those constellations you saw last night were going to also be in the exact same place. Or maybe if not daily, you would expect seasonal variations where you would see the same thing the next year and the next year, so forth. So there was this kind of paradoxical idea of both motion and the constant comfort of repeatability, right? So astronomy in the ancient world, so naturally, if this is your canvas, if this is what you're seeing every day out there, chances are you're gonna note down and write down what exactly you've been seeing, right? So this, we suspect, has been done by the entirety of humanity, regardless of what culture you are, where you are, probably right down to 40,000 years ago, or even 100,000 years ago. But the earliest records we have of people noting down the motions of stars and other celestial objects dates back to about 1000 BC. So this is a Babylonian tablet called the Mol-Apin Compendium, and it basically notes a whole series of stars and constellations and dates. After all, if every night you see this stuff, it makes sense for you to make a record of it of some kind. And people have been doing this in all cultures, right? You move forward maybe about 1,000 years or 500 years or so, and you start to get to the ancient Greeks. And then there's lots of ancient Greek astronomers and stuff who were really interested in the night sky. Here is this rendition of Hipparchus, who was often considered the father of modern astronomy, using some sextants and other tools to note down the motion of the moon and the sun. But we start to get this idea that maybe some of the stuff that we see is a little bit predictable, right? This constant dance of motion, but then this repeatability. And I want to complete this point by saying that, right, like to drive home the point that this was happening across all cultures. So you can go to the Aborigine people in Australia and you note that they also made recordings. You can go to the various dynasties of China, for example, the Tang dynasty here. Here's a star map from about 700 AD. And of course, you have the Mayan calendars, maybe some of us are familiar with, which predicted the end of the world in 2012, and all that jazz, which didn't end up happening, you can see. Okay, but what's maybe a little bit, what's reasonable about all of this stuff is that you have all these compendia and databases of these timings, if you will, but it's often hard to draw predictions from them, right? You have these complicated series of dates and times, but it's maybe hard to see or tell when something is going to happen next, right? You maybe can make some simple accrued extrapolations, or you have to do these very complex things to be able to figure out whether something might happen, whether you might see something in the sky 10 days from now, and chances are you may not, because you made some sort of small error in your extrapolation of reasoning from these databases. So this series of events persists for maybe about, I don't know, 1,000 years since those early astronomers, the Greeks, until a fellow by the name of Johannes Kepler. So Johannes Kepler was a German astronomer that lived around the 1600s. And then he used detailed astronomical observations that other people had taken, his contemporaries at the time, like you may have heard Tycho Brahe and others, who had made all these detailed notes. And he teased out some regularities that he later drew into laws. And so we call these Keplerian laws of planetary motion or orbital motion. And he identified that objects seem to move around in ellipses around larger bodies. So like planets move in an ellipsoidal or circular pattern around the sun. And he came up with a couple of other laws that relate how fast something moves around with its distance. And so he had these series of about 3 laws. But then it wasn't super mathematically firm, but it was enough to allow people to now start to make genuine predictions, saying, I understand the motion I've seen over here, which means now, 6 months from now, I know pretty much exactly where something is going to be. And this was all made possible by the Copernican revolution that had happened, where people had started to understand that the sun or the Earth was not the center of the universe anymore, and maybe the sun was the center of the universe. But it took another 80 years or so until a titan of physics came along by the name of Sir Isaac Newton, who used, basically, honestly, it feels like alchemy he used, because he used a combination of inductive reasoning and looking at some of these observations in Kepler's laws. And he came up with these laws of gravitation, right, circa around 1680, where we could write mathematical equations that related certain interesting properties. So forces, right, the pushes or pulls of planets or any objects, could be related now potentially to the masses of these planets along with certain distances. And it was a very dynamical process, because if 2 bodies, like these 2 bodies, M1 and M2, are interacting with each other and putting forces on each other, they're also moving at the same time, so also changing the distance between them. And so you have this cosmic dance, right? And so he firmed up Kepler's laws and put them on a mathematical footing. So now people could actually, with an intense amount of rigor, be able to predict things right down to the day, hour, and minute. Arguably, one of the most amazing predictions that came out of the so-called classical period, not classical, sorry, the period of astronomy in the 1800s, was the prediction of the existence of the planet Neptune. There was this, so the planet Uranus had been discovered in the 1780s by a gentleman, by an astronomer named William Herschel, which some of you in the audience may have heard. But Uranus is really far out, and it takes maybe about 70 years to complete an entire revolution across the sun, or around the sun. So it took until about 1840, until the 1840s, until people saw it back in its original position that had been discovered. But along that time, astronomers had noticed certain irregularities in the motion, right? Uranus was not exactly where they thought it was going to be based on Kepler's and Newton's laws. It lagged a little bit behind, or was also a little too fast at some points. So there was a French astronomer by the name of Urbain Le Verrier, and I'm butchering the name, but Urbain Le Verrier in the summer of 1846 said, I'm going to figure this out. And so he used Newton's laws and Kepler's laws, and he tried to figure out why Uranus was behaving so strangely. And he realized that the only reason that could be is because of the existence of another planet. And so he predicted the existence of Neptune. Nobody ever observed Neptune, but he said there must be a planet. So in the fall of 1846, he writes a letter to a German observatory. The name of the individual escapes me, but then he sends that letter. The day they receive that letter, the astronomers say that they go to their telescope, and that very night, within 1 hour of searching to the exact location predicted by Urbain Le Verrier in his letter, to write down to 1 degree in the sky, they find Neptune, which is an amazing feat, right? Because all these compendia, or databases of stars and motions that people had written, had been collected into these specific mathematical equations by Isaac Newton, which could then be deployed to predict what these heavenly bodies were going to be doing. And so this remains one of the big feats of this Newtonian Keplerian astronomy. Nevertheless, over the intervening maybe about 100 years or so, or actually 50 years to 100 years, other complications arise in the motions of close planetary bodies like Mercury, right? So people have noticed that Mercury in its orbit actually precesses, which means that its orbit, that this elliptical orbit actually kind of turns around the sun in a manner that was not necessarily predicted by Misters Newton and Kepler. But thankfully, there was a gentleman by the name of Albert Einstein, who some of you may have heard of, right, who came up with this theory of general relativity for other purposes, right? He was trying to understand some deep laws of the universe as it relates to gravitation, but folks pretty soon realized that this general relativity could explain this precession behavior of Mercury extremely well, and so then solve the problem. And so those complications that arose were swiftly put down. As a brief note, what Einstein tells us is that space and time are one thing, called space-time, and that matter curves space, so objects' mass curves the space-time, but then the motion of that matter is also dictated by the curvature of space-time. So again, another kind of cosmic dance where matter curves space-time, but then space-time influences the motion of that matter itself in a sort of cyclical pattern. So where does this leave us, right? So we have all these amazing theories by Newton, Kepler, and Einstein. It basically means that we can understand our solar system, right, all the close bodies around our sun, pretty extremely well. We can look at the motion of all the planets, like from Mercury to Pluto, and we can predict where they're going to be, where all their moons are going to be, where all the tiny asteroids in between are going to be, to extreme precision, such that we can send spacecraft right there, and we know that they're going to end up there, no questions asked, right? We've all seen amazing pictures from spacecraft that have landed on the smallest little asteroid out there, and all thanks to Misters Einstein and Newton. One point I want to make here as a definition, if you will, is that we often talk about distances in a special way in astronomy and astrophysics. And so the unit I'm going to introduce to you is something called the light year. Light is very fast. Light is the cosmic speed limit. Nothing moves faster than light. And that speed is 300,000 kilometers per second. I use metric because a lot of scientists use metric, but it doesn't matter if you think in miles, maybe about 200,000 miles per second. Really darn fast. Yeah? So you can use that speed to define distance as well, if you think about time. So 1 light second is how long it takes for light to travel in 1 second, right? That's 300,000 kilometers. 1 light minute is equivalently how long it takes to travel in 1 minute. Light hour in an hour, and light year is often a standard unit in astronomy, how long it takes light, 300,000 kilometers per second, to travel a distance over an entire year. So it's unimaginably large distance. The sun from us, in these units, is 8 light minutes away from us. Light from the sun takes 8 minutes to reach us. Light from the sun to Pluto takes 5 hours to reach Pluto, right? So it gives you a sense of scale of how big and vast the solar system is. but we're still talking about light minutes and light hours. We can, of course, take a step back, right, and then look. Our telescopes not only show us the close planets, right, of the solar system, but then also allows us to understand our local neighborhood, what we call our Milky Way, the galaxy we live in. So a galaxy is a huge cluster or combination or amalgamation of stars in there, much like our sun, some bigger, some smaller, and there's a black hole at the center, which we won't talk about. But basically, our observations allow us to understand this galaxy that we're in. And this galaxy that we're in is 100,000 light years wide, right? We were talking about light seconds and light minutes and stuff like that. This galaxy that we live in is 100,000 light years in diameter, roughly, and contains over 100 billion stars in it. Estimates vary, but then that's the order of magnitude you should be thinking about. And then we can map out, like our local neighborhood. So the sun is about 2/3 of the way out from the center. And we can see other dwarf galaxies and other small objects orbit it. And we can use our known laws of physics and astronomy as they've evolved to sort of basically build a model, even though we live within the Milky Way. Looking a little bit further out though, right, we see billions of galaxies like this. So this, for example, is something called NGC 4414. It's just a naming system, the galaxy catalog number 4414. It's not a particularly exciting galaxy, I want to say, but it's incredibly pretty. And we see this one 62 million light years away. We had been talking about 100,000 light years wide galaxy. Now we're talking about tens of millions of light years away, another galaxy out there. And looking at images like this is what helps us understand our own galaxy. And this specific image was taken by the Hubble Space Telescope in 1995. Okay, so like I said, it allows us to understand the classical spiral structure of galaxy. And the other thing we notice is that these galaxies tend to rotate and turn, right? And so that they're always, they're spinning, and so then there's that motion associated with the rotation of galaxies. As a brief note, right, we've been able to map out all of the universe thanks to some of these amazingly engineered devices that humanity has been able to build, such as the Hubble Space Telescope, which is the size of a school bus out orbiting the Earth, and which has amazing mirrors in there that can focus the smallest amounts of light. But of course, there's hundreds of these telescopes out there. The most recent enormous one is the James Webb Space Telescope, which folks in the audience may have heard was launched semi-recently and then has started taking data as of the last few years. You also have massive ground-based observatories. So this one is called the Giant Magellan Telescope. That'll be built in the Canary Islands. It's being built in the Canary Islands. We'll start collecting data in about 2030. And it has a 30-meter wide collecting area for light. So it's huge, right? Like it's bigger than this, almost bigger than this room in terms of how wide these mirrors are. And so those mirrors allow you to focus all that light and collect it and be able to see some of the furthest things away in the sky. Also, interestingly, we can see across the whole electromagnetic spectrum. What do I mean by that, right? We can not only see stuff in the optical, like using regular color that we can see with our eyes, but also extending out into like infrared radiation or X-rays or radio waves. So we have the technology to peer at the universe across a whole spectrum of different kinds of light. So maybe about in the mid-90s and also continuing on to 2000, the Hubble Space Telescope stared at what looked like a dead patch of sky. The size of the patch of the sky was if you held our hand out and the size of your fingernail, that's the size of the patch of sky that Hubble stared at for 10 days, collecting as much light as it could. And in the 90s, people didn't expect that the universe was going to be, or figured the universe was going to be kind of a dead-ish place, right? That we would see maybe a few galaxies and stuff like that, but we wouldn't see a lot. Turns out, this is just a fraction of the image of what Hubble saw. We see a universe teeming with galaxies and structure and interesting objects all over the place. So we see tons of galaxies, and we can see all this phenomena predicted by Einstein of light being bent because of these massive masses. And we can see this cosmic dance. And what this tells us is how remarkably crowded the universe is. But also, it gives us a handle into understanding the origins of the universe. We can use the laws of Einstein and some of these observations and build up what we think is the history of the universe in time. And we believe that the universe started in something called the Big Bang, maybe about 13 billion years ago, where all the energy of the universe was compressed into a single point, which then expanded out dramatically. And then you have all these interesting features, such as when the universe became transparent to light, because up to some point it was pretty opaque, light couldn't travel, eventually it became transparent. And so we can see that afterglow from about 375,000 years. We call it the cosmic microwave background. I'm just telling you it as a little bit of a definition because I'll bring up that concept, but it's not necessarily the focus of this talk. Regardless, so we're at present day where the universe we see is about 90 billion light years wide, right? That's our best estimate. We've been talking about light seconds, light minutes, now we're talking about billions of light years wide. And we think the universe is about 13 billion years old. And so this is an absolutely wonderful thing, right? We believe we understand a lot about the universe. We've built these amazing toys like the Hubble Space Telescope and all these giant Magellan Telescope. And we think we understand the motion of all these bodies. We're able to predict the motion of planets and a few stars and stuff to extreme detail. But then there's a problem lurking around there, right? There's always a problem, as everyone knows. But I don't want to be too glib about this, but people have known this problem that I'm going to talk about for about 60 years now. And so a lot of the theories that I showed you in that graphic of what we understand the history of the universe has also had to grapple with this problem. And so it's been a balance where this problem has influenced some of our thinking. Spoiler alert, that problem I'm going to tell you about is this concept of dark matter that I'll introduce in a slide or two. But then before we get there, why don't we do a little bit of a thought experiment, right? If I asked you, how do you measure the mass of a galaxy? Again, I told you at the beginning that this was not going to be a super interactive lecture, but here might be a point where I can just ask the audience in general if folks have any idea of how you might measure the mass of a galaxy, right? Because it seems very simple on Earth. If I wanted to measure the mass of an apple or how heavy something is, I can use a spring scale or something like that. Tells me it's a pound or so. But something that's 100,000 light years wide, composed of so many darn stars, how do I tell its mass? Does anyone, while I take a drink of water, does anyone want to ponder that for a second and then maybe shout out some answer of what you think, maybe based on what you've heard or seen in
maybe
your
you can
readings?
count the number of stars and model the amount of gravity they have with each other.
Sure, yeah, excellent.
How fast it spins.
Yeah. Right, so I've got the two answers I was looking for, so time to move on, I guess, right? So there's this notion that maybe if we understand how heavy some of the constituent objects are, some of the stars, we can be able to tell how heavy the composite must be, right? It should be equal to the sum of that stuff. Also, if you remember from the slide about Newton, we introduced this idea that motion tells us something about the mass. So anytime you can talk about the forces and motion of an object, that's related to the mass in this concept of gravitation. Which is exactly this idea that some of you have pitched, right? You can use some of these tools by Kepler, Newton, and others to figure out what the mass of a galaxy is. So one neat trick that to use the suggestion set out front to determine motion is to exploit something called the Doppler shift. This is a very interesting phenomenon, that if you have objects that are moving relative to each other and one of them emits light of some kind, depending on how fast the relative motion is between these objects, the color of that light is going to be slightly different, right? So we're talking about really fast speeds. We're not talking about necessarily measurable on a human scale, but then if you got things that are moving pretty fast. Objects that are moving closer to the observer look a little bit bluer than if there was no relative motion. The wavelength of the light is squeezed a little bit. Objects that are moving away from you are a little bit more stretched, right? So it's redshifted. And this technique is called Doppler shift. And so you can look maybe at a spinning galaxy and then see how much the side moving away from you is redshifted versus the side that's moving towards you is blue shifted, and figure out some relative velocities and then use the physics that we introduced previously to be able to estimate the mass of this stuff. Additionally, you can use the suggestion from the middle of the room, right, where you can think about the constituents, and we've used this Doppler technique to measure the mass of stars, right, that are in the close neighborhood, and we've realized that the mass of stars basically is very tightly linked to how bright they are. The brighter an object a star is, the heavier it is, and it's borne out by some of these precise velocity measurements. So it seems obvious that if I added up all these stars, I would be able to get the velocity or the mass of the galaxy. And if you predict from the summing up all the masses of the stars how fast these galaxies should turn, you get this curve over here, where it says the distance from the center of the galaxy on the x-axis, you should get this curved shape like that. As you go further away from the center of the galaxy, things should slow down because you're basically running out of, like the mass tails off from how bright the galaxy looks in the center. People have looked at this, and particularly in the 1930s, people have applied these techniques. There was a gentleman, an astronomer by the name of Fritz Zwicky, who was an astronomer at Caltech. And he applied this principle to clusters of galaxies, because at the time it was easier to look at the relative motions of larger objects, of galaxies versus each other. And then he attempted to compute the relationship between the mass and the brightness of these structures, and he found a number that was completely out of whack. They were expecting these ratios of mass to light to be in the order of about 5 or so, or small numbers like that. They measured numbers like 300 or 800. These objects were behaving like they had 300 times or like 100 times the mass that you would expect, just from summing up how bright these objects looked. But this was the 1930s. People had just discovered the neutron. People didn't know how the sun worked. So then people figured, you know what, this is all just, maybe it's a little bit bunk experiment, right? We don't understand our telescopes. We don't understand physics in large scales. It's not a problem. We'll eventually figure out what's going on in the future. Well, you move forward another 30 years or so. You have an intervening world war, which puts a pause on a lot of astronomy. After the war, there's a huge explosion in technology. People build better telescopes. People understand more about the systematics and experimental errors that might crop up in astronomy. And then there's a scientist by the name of Dr. Vera Rubin, who works at the Carnegie Observatories in Washington. And she and her colleagues take incredibly careful systematic studies of the motion of galaxies, right? They are trying to show that the galaxy rotation curves, how fast the galaxy spins, follows this line A, like I showed, based on the brightness of the galaxy. Instead, using this Doppler technique, they find that those rotational curves, the speed at which the galaxy is rotating, look really weird. They rise up as expected, and then they plateau, which is bonkers, right? It does not match Newtonian expectation. It does not match general relativity. It's just completely weird. And this was not an isolated case. Basically, every galaxy that they looked for, and all collaborators in everyone in the world was searching, well, it wasn't a huge effort, but then everyone who looked saw galactic rotation curves that looked weird like this. They didn't follow your Newtonian expectation. This laser pointer is a bit wonky, but they didn't follow this up and down motion. So, what might be going on? Well, it seemed that galaxies were behaving like there was this halo or like collection of non-luminous matter. That most of the mass of the galaxies, in fact, the majority of the mass of the galaxies, didn't seem to be in the stuff that was glowing, but was instead in something that was dark and that we could not see, but was affecting the speeds of all the objects that rotated within the galaxy. And so naturally, scientists didn't necessarily know what to call this, and so they parameterized their ignorance as dark matter, right? Dark matter isn't anything supernatural, or as maybe our television shows would like to point out, of something alien or whatever. It's just this ignorance on our part. We have observations of the universe which do not match the stuff that Newton and Einstein and others predicted. Laws that work incredibly well on Earth. I can predict the motion of atoms. I can predict the motion of my baseball, like if I threw a baseball, right down to like the 10th decimal place in some cases. But this same stuff doesn't seem to work out in the universe, and it makes us think that there's this whole amount of missing matter and missing stuff out there, which is incredibly weird. So what's going on? Well, to nail home the point, it seems that this dark matter stuff is not just in every galaxy, it's everywhere in the universe, permeating the universe. It's in our Milky Way as well. In fact, it's passing through us right now, depending on the models we use for thinking about this dark matter. It's going through Earth as we speak. It's so diffuse and not very dense that you can't really notice its effects on very small scales like even the Earth. You have to think about galactic scales for you to be able to notice this change in motion. But then we have a lot of galaxies, we have a lot of evidence. This is not the only evidence we have for weird stuff. Since the 70s, we've been looking at other interesting features in the universe. We've looked at colliding clusters of galaxies, so huge objects which kind of pass through each other like floating clouds of gas and stars and stuff like that. And we can look at their mass and their luminosity in a couple of different ways. We can use this interesting technique called gravitational lensing predicted by Einstein. The idea is that if I have a massive object, and then I'm not going to shine a laser pointer in people's eyes, but then you have a light source behind it, because mass curves space-time, the light that's emanated actually curves around that massive object. And if you detect the light on the other side and you can tell that it's kind of curved, you can then tell the mass of that specific object that did the curving. So people have looked at these colliding clusters and seen that the green contours here show where the gravitational lensing tells you where the most mass is in these contours right here. But we can use our telescopes and look at light, including X-ray light from this stuff, and that says most of the glowing stuff is over here. So there's a disconnect between where one method tells us the masses and another method tells us where all the stuff is. So it looks like in this collision, these two things collided, but there's some component that doesn't interact a lot, that kind of pass through each other, while all the gas, which does collide with each other, kind of slowed down in that interaction. So this is further evidence maybe of this idea of some unknown material out there that we've parameterized our ignorance as and called it dark matter. I'm gonna maybe skip this slide a little bit, but I won't. Remember that afterglow pattern I told you about 375,000 years after the formation of the universe? It's called the cosmic microwave background. It's this idea that the universe was opaque prior to those 375,000 years, and at that point it became transparent. So all the light that was in there finally could free stream out without being stopped by anything. And we can record this stuff on Earth using some radio telescopes and the like. And in fact, 1% of your TV static in your old analog TVs was actually caused by the radiation that comes from this cosmic microwave background. The point of this slide anyway is to tell you that people can't get that really cool model of the universe, evolution of the universe, without assuming some dark matter component. You need dark matter to be able to make all the rest of the physics work in understanding that 13 billion year history of the universe. Okay, so I've told you that there's this weird stuff called dark matter. Your natural question would be, what exactly is it, right? So in the 80s, right, when people had finally realized, oh, well, something's weird, the most reasonable explanation seemed, fine, there's a ton of mass or matter in there, but it's just not glowing like a sun, right, or a star. It's just kind of dead. So it might be dead stars or floating rocky bodies or small stuff that's just everywhere. And this was called the massive compact halo object hypothesis, or MACHOs.
Let's spell GGG junk.
Oh, lots of big junk.
That's big.
It's just
I thought it was an L.
oh no, it's just the capitalization. Lots of big junk. No problem at all.
Okay, now that was that was an acronym.
Yeah. Okay, so people think it was just this floating junk out there. Alternatively, some other people in the 80s and 90s said, you know what? Much like Newton first did, and then much like Einstein did, maybe our laws of gravitation are wrong, and we have to expand our laws of gravitation. So then there was this attempt to derive new laws of gravitation, extend Mr. Einstein and Newton. And one example of this technique, this mathematical technique, is called modified Newtonian dynamics. And it says that those force laws that we talk about are modified ever so slightly. The third arm, if you will, is that there's new physics, much like point number 2, except it takes the form of unidentified or new subatomic particles that only interact gravitationally, but hopefully in some other ways potentially, so that we can detect this not just using gravity. But basically this dark matter is composed of tons of subatomic particles that are very, very hard to detect, and mostly make their presence known through the gravity that they create in bulk, right? So instead of the stuff that we know and care and love about, like, oh, actually I don't have a subatomic particle chart here, it doesn't matter. Protons, electrons, and all the stuff that we know. There's this stuff that makes up, similar to that's what dark matter is. We can grade these explanations in a manner of speaking, right? So this idea of machos is great because it doesn't require any new physics. We're talking about matter that we know, just that it doesn't glow. It's been mostly ruled out by some of these gravitational lensing studies. People look for all these deformations, and we've got really, really sensitive equipment now. And statistically, it doesn't seem to be the answer. It doesn't also work a lot when you talk about universe formation. It's hard for my colleagues anyway, who are theorists. I'm an experimentalist, so I work in a lab. But the folks who do the actual math say it's hard to actually make galaxies form naturally over the timescales we care about. It's hard to make the universe behave as we see it now, if we assume machos. Modified gravity is also great. It explains rotation curves beautifully, right? Mond and all these other theories can help, by changing the laws of gravity ever so slightly, can help explain these rotation curves beautifully. However, it doesn't do so well in the large-scale description of the CMB and the universe. And also, it's hard to make a relativistic version of these theories. They're great in explaining Newtonian effects, some Newtonian effects at large scale, but nobody's ever made a relativistic version which works with general relativity.
Well, what is CMB? Did you say?
Oh, sorry, cosmic microwave background, which is this,
Oh yeah, you mentioned that's
Yeah.
fine. Yeah, that's good.
So, the machos probably ruled out. Modified gravity, lots of people still work on this sort of stuff. It's open, it's an interesting idea, and there's recent work that people have done to show maybe some of the CMB effects could be explained by changing the theories of gravity. But the particle dark matter one seems to be the most, the one that fits in most with the known laws of physics, right? It can be engineered to work well with all known data. However, some of the cons are that the theoretical modeling can get pretty hairy. You're trying to invent this new particle, and your constraints on what it could be are so loose, if you will, that you could introduce a lot of accidental physics you don't want. And so there's a little bit of a fine-tuning problem there, maybe. But it's all just this idea that we don't actually know what it is. But the laws of quantum mechanics and our understanding of the subatomic world on Earth is so amazing, right, that we can predict things like nuclear reactions to an extreme level. So we feel most comfortable in saying that dark matter could be or is an extension of some of these fundamental quantum mechanical principles and laws, and so is a particle of some kind. Okay, so what is the standard paradigm here? How can we explain all the wonderful and wacky features of the universe? And how can we extend these laws of quantum mechanics, quantum field theory, and the particles that we care about, of asking the question of how can we go beyond the standard model of particle physics in a way that makes sense? And my scientific forefathers in the 1990s came up with this idea of a weakly interacting massive particle called a WIMP. And it was a kind of a cute joke because at the time machos also were a big thing, so it was the big fight between machos and WIMPs. So the's things are kind of like very, very, very heavy protons, if you will. The mass of a proton in some unit is 1 GeV. These things were thought to be about 10 to 1,000 times bigger than that of a proton. Yes?
Those are supersymmetrical particles you're talking about, is it?
Yeah, so it's introduced, which is part of the reason of extending the standard model of particle physics, was bringing this idea of supersymmetry to answer some other problems which I am sweeping completely under the rug about particle physics. So you can talk to me after about that stuff. Okay, so how on earth could we figure out if it is one of these particles like this? Well, we hope that maybe these particles can actually interact or like, you know, affect the standard model or like regular matter that we care about. And so people draw this kind of diagram, which is more of a cartoon than anything, that says, what happens if you have two dark matter particles that you have on the left and the blue, and then time moves in the direction going right? You have these two dark matter particles smash into each other in some form and create regular or standard model particles of some kind. So maybe somewhere where there's a high density of dark matter, like the center of the galaxy, you could have a lot of this annihilation events, which spews out a lot of very, very high energy regular stuff like light or X-rays and stuff. So we have telescopes staring at the center of the galaxy, looking maybe for any signal. Some people say they've found something, others say absolutely no way, we have not found anything yet. But that's one way of looking at it. You can run this diagram in reverse and say, what happens if I smash together some standard model particles at very, very high velocities? Which should put you in mind of things like the Large Hadron Collider at CERN, which does exactly that. It takes protons and smashes them at incredibly high speeds, and then scientists there look at the resulting products and try to figure out what might be created in that whole mess. And maybe something like dark matter pops out on the other side. The other way you can do it, and this is the way I work, or the field I work, is we can read this diagram going upwards, where a dark matter particle comes in, you have some sort of standard model particle, maybe an atom or something like that. This dark matter particle scatters off of it, deposits some energy in there, and then changes the system. And so maybe I, as an experimentalist, can measure those tiny changes, those tiny deposits of energy, and then try to work back whether we actually detected something from out of this world. So the basics of it is very simple when you dial it down of this field. You want to take large vats of something or large amounts of material of some kind. It can be a crystalline material, it can be vats of liquid xenon or something very pure, and something that if you were to perturb it by having some external particle come and smack into it, will give off a burst of light, a burst of electrons or something, and then you as an experimentalist now can collect that light, collect those electrons or stuff like that, and try to figure out the energy and details of the original interaction which deposited that energy, right? So, at its core, it's a very simple thing. I want to instrument a bunch of regular stuff and put it somewhere deep, dark, and quiet, and wait to see if I see any unknown flashes of light or other perturbations of said sensor. One problem, anyway, with all of this is that it's been 30 years of null searches for WIMPs. People have been thinking about this stuff since about the 90s, which is 30 years from now, right? Experiments put out these curves regularly, where this is sort of the plot that in my field that we look at a lot. On the x-axis is the mass of the dark matter particle you're thinking about. On the y-axis is how strongly it interacts. And these searches have continually come up and have not seen anything weird. And so they constantly push down these lines which say that the interaction cannot be that strong, it must be weaker, and so we rule out this parameter space. So the situation is maybe a little bit head-scratching, where we're not exactly sure what the future holds, but what that means, though, is that maybe we have to loosen our following of this, or our thinking that the dark matter is these WIMP-like particles. In fact, our theory colleagues suggest that the landscape of what dark matter could be is actually very, very huge if it is a particle. It could be, so I said in this units of GeV, a proton is 1 GeV all the way at the right. You could have dark matter particles, theoretically, that are 1 followed by 30 zeros times lighter than that. Equivalently, you could also have dark matter particles, it's perfectly consistent to write down these mathematical models, that are 1 followed by 30 zeros times bigger than that scale that I was talking to you about. So it's the Wild West out there, right? we have some rules about how this stuff can interact with, because otherwise the rest of the physics that we know and can make calculations with breaks down completely. But then, in terms of its, particularly along this axis of mass, it could be anything in there. And so, how do we now grapple with this landscape? Well, we develop new and interesting experiments to try to target some of these mass ranges over here. So I've just thrown a few names of different acronyms for experiments out there in the world that are trying to look at different regions of this parameter space. And they run the gamut of different technologies. And so you have your classical, like this experiment called Lux over there. It's just this giant vat of xenon, which people are staring for these signals from. You have this ADMX, which is this resonant cavity. Not necessarily going to talk about it in any detail, but it's just another style of looking for something very, very, very light. A dark matter particle that's very, very light that maybe converts to photons within this cavity. Or you can, instead of a liquid or a cavity, you can also maybe have a solid crystal of some kind. So there's a germanium crystal in this super CDMS experiment that's looking for very tiny vibrations of the crystal. But the name of the game fundamentally is you're instrumenting some object and you're waiting for small signals from it. Naturally at this point you can ask, how do you know that if you see something from this experiment, it's actually dark matter and not just junk that's around you, right? It could be natural radioactivity. If I eat a banana, right? A banana has potassium-40, which is a radioactive isotope that'll decay, that'll spit out some alphas, I think, and that can actually trigger your experiment. So the way you do this is you institute a rule that nobody can eat bananas besides your experiment. But also, right, you have to make it incredibly clean and pure and put it deep underground. And the reason you put it deep, deep underground is because then cosmic rays and stuff that are on the surface cannot make it all the way down in there. So for example, here is the Snow Lab facility in northern Ontario in Canada, which is 2 kilometers under the ground. And it's actually a working nickel mine. So to access this facility at 6 o'clock in the morning, you got to go down with the miners in their mining elevator. They get off on one floor. You continue down in your full get up over here, looking much like the miners that work in the mine. You trek half a mile, and all of a sudden you come across a set of double doors. You walk in there, and on the other side are these incredibly clean underground facilities which are like basically clean rooms. You have to strip off all your clothing, take a shower, and get into some pretty fancy garb to be able to access these labs underground. So the name of the game is you take these really sensitive experiments and put them as far away from anything that could disturb them, and you try to see if there's some weirdness that happens. Okay, so I've spent maybe about 45 minutes leading you or guiding you towards this idea that we have potentially some unknown physics out there in the universe. We cannot describe what's going on. We have parameterized and called this ignorance dark matter, and we've come up with a whole bunch of different ways of maybe trying to determine what this dark matter is through experiments. And so now in the last maybe 15 minutes of this talk, I'm going to tell you about a project that I work on and will continue to work on at WashU. One of these experiments that I've pointed at in the past, but it asked maybe the slightly provocative question, what if you could take a picture of dark matter? And based on everything I've told you right now, you should shake your head and say, that sounds ridiculous. There's this unknown material. How the heck could you actually take a picture of it? And I'm only being semi-facetious when I say this. But the idea is we could use charge-coupled devices, or CCDs, as our sensor. So I'm assuming nobody, or only a few of you maybe know what a CCD is. CCDs are these exquisite electronic devices which form the heart of modern-day cameras. In the past, it used to be, right, when you took a picture, it was some photo film, some like chemical film, which then recorded the picture. Nowadays, it's this piece of electronics called a charge-coupled device, which actually registers the light on those devices and is able to recreate the image. People have noticed that when you take pictures with some of these high-end CCDs, you notice interesting and weird tracks on them, right? And you can say that this is all just junk, right? That it's some artifact, electronic noise, or whatever. But people realize that all of these are actually particle interactions that you've been imaging. So this streak over here actually comes from a cosmic ray of some kind. These wiggles over here come from random electrons that have entered into this device. And so these CCDs are actually a very interesting way, or allow you, in a sense, to image particle interactions. So the natural question, or actually to move it forward, what exactly is this technology? These are maybe about 9 centimeters wide or rectangular in shape, the devices that we use. They're divided up into very, very tiny pixels. And this is how actually, you know, when people talk about megapixels of a camera, it just means how discretized these sensors are. And the analogy I like to use in the CCD is that it's basically like a conveyor belt of rain buckets collecting rainwater. Light comes in some fashion, triggers or fills up these buckets, and then you move the conveyor belts in a certain pattern, and then you read out the amount of water collected by each bucket, and then you can identify where that bucket came from, and so you can reconstruct, right, an image of rainwater, but also of the light that produced an image. So the standard imagers that you have in your phone are using complementary technology to these CCDs, but they're maybe about a millimeter in size. We're talking about giant CCDs that we're using. You can look at a cross-section of an individual pixel. So these CCDs are maybe about 0.5 millimeter thick, so 500 microns to 650 microns. And each pixel there is about 15 microns by 15 microns, so that's about the thickness of a human hair. So each pixel in there is very, very thin and narrow, and it's basically just a lump of silicon instrumented with some voltages there, which will allow you to actually talk to and read out the CCD itself. Our expectation, our hope, right, in using these devices is that if, not necessarily a dark matter particle, but if anything of some kind comes and scatters and interacts with the bulk of the CCD, you end up liberating those electrons from within the silicon. And so now you've liberated some charge within the device. And then I told you that we apply some voltages to this device. So you can go ahead and use those voltages to drift those electrons up to the top of the CCD, where you can then end up collecting them. And then you can move this charge around and then try to read it out in that same analogous to that rain buckets on a conveyor analogy that I was using earlier. So you judiciously change the voltages, and you're able to read out these devices. So what do you see when you take an image with one of these CCDs? You see a lot of static looking things, which is just electronic noise in the system, but you also clearly see if an external particle of some kind, external subatomic particle of some kind, has come and interacted with your device, or like passed through. Yes, sir?
What are you focused on?
You're not focused on anything. That's the thing, right? You've put this thing deep, dark, underground,
Okay.
where you can see no light. Because the idea is we don't want to see anything else. We want to see maybe this dark matter particle that's around us at all times, that comes and scatters off. You can use this to identify a bunch of things which are obviously not dark matter, right? Anytime you see a streak like this, it's a muon, which is the subatomic particle maybe created in the atmosphere that streaks down. You can see those alpha particles or electrons that are created by the banana that you were eating beside your device. What we're looking for anyway are these tiny low energy blobs, which might herald the signature anyway of a low energy interaction that comes from dark matter scattering with your detector. You can use some clever readout techniques to get rid of this static looking background in there by repeatedly reading out each pixel in a non-destructive fashion. So just for academic interest, you can have these clever electronics which allow you to read a pixel multiple times. And so I now have this section of an image that I'm showing here in a few colors. If I keep reading out the pixels on it repeatedly, I can see that the distribution of the pixel quantities keeps getting narrower and narrower. And if I continue reading it out, the same pixel, thousands of times, I'm able to clearly tell whether a single pixel contained 1 unit of charge, 2 units of charge, 3 units of charge, and so on. And so these detectors provide exquisite energy resolution, which will allow me to tell details about any potential interaction that has happened in the device. So this DAMIC program, Dark Matter and CCDs, has actually been running maybe about for a little under a decade right now. It started as a very small project in Fermilab in Chicago. And the latest iteration of this experiment we are putting in France, in an underground laboratory in France. So here are some pretty pictures of collaborators building these devices. You can see the CCD in the bottom left corner. And so then you have all the support electronics and shielding to prevent any external radiation from coming in. As a quick note of this Modane facility, it's located in the border between France and Italy, and you could go deep down underground. Alternatively, if you went into the side of a mountain, you have all the overburden, which helps shield you from the outside world. And so this is exactly where this lab is located. It's actually really easy to access. You just drive through a tunnel, and then you pull off on the side, and you have one of those clean room facilities that, instead of going all the way down into a working mine. So this is some more pretty pictures of the DAMIC program. At present, you can see here inside this box, so there's no light. It's not exposed to light at all. It's completely sealed shut, because the idea is this dark matter so weakly interacts with anything, it's not going to be stopped by anything, and very, very, very occasionally might interact with real world matter, and so you hope it basically interacts with your device. Here are some more pretty pictures about the rest of the support stuff. You have some radioactive shielding of high-density polyethylene. You have some of the vacuum pumps and cryogenic coolers, which get you down to the operating temperatures that you require. And in the last year or so, we've been running this experiment. And fortunately or unfortunately, we haven't seen anything. Unfortunately, in the sense that obviously we would like to see something, because it means that maybe we've detected something interesting. Fortunately, because it means that we probably did a very good job in shielding our devices so that that aforementioned banana that I keep mentioning has not contaminated our data. So we published a recent set of results. This is more just me flashing some plots up there of those exclusion plots I briefly touched on earlier in the talk, where we ruled out certain parameter space for some dark matter candidates. And in the future, we're going to go even bigger and bolder. We're going to have 10 kilograms worth of silicon. We're going to improve the energy resolution of these devices so we can hunt for new parameter space and look in a different corner for what the universe might be hiding. And I want to stop there effectively, but I do want to talk a little bit, the last slide or two, about what the future holds here, right? So we've come on this journey where I've told you about the amazing work done in astronomy and astrophysics and being able to predict the universe. We've realized we don't know what we're talking about. There's this huge missing gap. It may be a particle of some kind. It may be we don't understand our physics of some kind. But it's just this huge open problem. And where do we go from here? We're obviously going to continue building bigger and bigger experiments to try to find this. Our theory colleagues are going to work on more interesting mathematical models, maybe refine our understanding of what gravity is, and hopefully we solve all of this. But I want to leave you maybe with parable/analogy in that the ancient Egyptians used to know about electric catfish, right? People would actually go and be shocked by these catfish, and they reputedly used the electric shock from them when treating arthritis pain, right? They didn't know what the heck, why they were getting this jolt when touching it, the stuff. They couldn't explain any of that stuff. They thought these were magical creatures, but they actually ended up using it for medicinal purposes. It took about 4,000 years from that point, right? In the 18th century and stuff, for people like Benjamin Franklin, Alessandro Volta, Michael Faraday, and other luminaries to begin to understand what electricity was, to try to figure out what actually is making all these sparks, what's happening in these catfish and frogs, and why are they twitching in weird ways, and I'm flying my kite, what exactly is lightning? It took another 140 years before people actually could harness electricity, from the time of Ben Franklin anyway. It took until the 1880s and 1890s until people could build light bulbs out of it. This is a picture of the White House as instrumented with electricity and light bulbs. So we've now taken so long between some of these individual steps, right? So the idea that I want to leave you with anyway is that we may have to keep thinking and searching for dark matter for a long time. We've known there's an anomaly for 60 years. We have only really understood the details of that anomaly in the last 30 years or so. We're maybe at our infancy in trying to probe what this puzzle is. We'll keep working at it, but it may take generations. Hopefully it doesn't take 4,000 years. Hopefully it doesn't take 140 years, because I would like to see this resolved in my lifetime, and hopefully in all of your lifetimes. But it may take still a while for us to figure out what the heck is going on. So with that, I appreciate all your listening. Thank you, and I'll be happy to take any questions.
So I was wanting to know what your email was, because I'd like to check out your research.
Oh, sure, yeah, so I'm happy to provide that.
Can you repeat the question, please?
Oh, so it was asking for contact information to ask specific questions. Pardon? Oh, yes, I can absolutely, there's no chalk because they hide the chalk in this room. What I can recommend you do, there's my name. And you can look me up on the website, and all my contact details are the WashU Physics Department website. Yes, we'll go onward.
This model of dark matter would mean it could occupy the same space as regular matter, right? Sort of like a boson's can occupy the same space.
Yes, and so we consider, so in technical terms, there's my son. Thank you. So in this language, we talk about like baryonic matter and non-baryonic matter. So baryonic matter, anyway, is like the regular kind of matter that we're accustomed to. This is all non-baryonic matter. And the important thing here is that it interacts so infrequently that it can occupy some of the same space. I know you didn't ask, but the dark matter itself could be fermionic, in which case it has to obey certain rules internally about occupying the same state or not. But that is some internal rules that it has to follow. Yeah, actually, sorry, you first, please.
I have two questions, actually.
Sure.
One is, if dark matter can comprise half or more of the mass of the universe, I've seen articles that say that.
Yeah.
Why are you looking light? Why wouldn't you be looking heavy?
Oh, one note of caution there anyway, or clarification maybe, is that sometimes when I refer to light, I mean light in terms of the particle itself, but in aggregate it's very, very heavy, right? But I think to get to your point, people do care about very, very heavy things, right? So it could be, one idea is that all of this dark matter could be black holes of some kind, right? Like supermassive black holes that are 10 times the solar mass, 100 times the solar mass. But then one of the neat things we have with all the telescopes and stuff that I've told you is we can look for some of these things even if they don't glow. So we can do those like microlensing or gravitational lensing studies. So we have some light being shined by some object in the far distance. There's this massive object, maybe this black hole that we talk about, and then here I am with my telescope looking at it. This light is going to be bent in certain ways around it, which will allow me to tell details about this intervening object. But importantly, this doesn't matter if this thing is glowing or not. If mass is present there, it'll do this bending thing. So we can look all over the sky, and we have to draw some statistical inferences, right? Because you can only sample some of the sky. But we've been able to more and more rule out the explanations of very, very heavy objects that are not glowing.
And my second question was, and I almost have the answer to this, but
Yes.
why do we care?
Why do we care?
Yeah, I mean, if classical physics
Yes.
describes the planets and
Yeah.
all the stuff we need to know these days,
Yes.
I mean, yes, you can say, yeah, the Egyptians used electric eels, it took us 4,000 years to figure out why. So maybe in 4,000 years we'll have a practical use for our knowledge of
Yes.
dark matter. But why are we expending, I mean, the cost of digging down hundreds and hundreds of feet and workers building clean rooms, I mean, you're talking billions of dollars for these things.
Yeah.
To what end?
Right, so the answers I may give you may not satisfy you, but it does come down to like understanding what the universe is made of, right? Like it's been a driving force for humanity, right? If we'd had the same notion 1,000 years ago, maybe we would still be living like Romans, right? Maybe we wouldn't have the technology that we do now. And so it's this fundamental pursuit of science, right? It's like we keep asking the question, why, how can we understand what's happening? And like you say, right, maybe we only get the benefits of this from 4,000 years, but then if we don't start now, maybe that clock for 4,000 years only starts whenever we do start. And finally, the point I want to make is that this stuff is not actually super expensive in the sense that we're using mines that are already built, right? So it doesn't end up being a huge number, and these experiments are pretty small, right? Like it has a team of scientists, but we're not talking about like a space telescope costs $1 billion. We're talking about like tiny fractions of that with the potential to revolutionize something we completely don't understand that makes up a majority of the universe.
It's not as expensive as it sounds.
Yeah. Sorry, you had a question, yes?
You mentioned on the describing the experiment,
Yeah.
the cryogenic aspect.
Yes.
Why is that important?
Oh, so depends on the technology you use. So in our particular experiment, we're using these CCDs, these electronic devices, which have a lot of inherent noise, which we call like dark counts, so to use some technical jargon, and that gets better the colder you make these devices. So we want to go down to about 90 Kelvin, minus 180 degrees Celsius, so we use some technology for that. I don't remember the order of questions, and so I'll go with you in the back, yeah. And then we'll come to you in green.
Yeah, you've showed us nice examples of how many different groups and experiments are going on,
Yes.
looking for relatively small, relatively big, no one's come up with anything.
Yeah.
What experiments are being done for the opposite question, that ain't nothing missing, we just got the theory wrong or incomplete? I mean, to me,
Yeah.
we thought we understood everything, and Newton and Einstein said, you move really fast, stuff changes. Why are we ignoring it? If you have really huge distances or mass, we don't get it.
We're not necessarily ignoring that, absolutely. What it is that people come up with theories, right? And so there's a couple of things that those theories need to go. They first need to be internally consistent, which can be done. Then they need to not clash with any other known laws of physics, right?
But why is that? Relativity clashes with, you know, the very small, for example.
Other laws of physics that we have strong predictions for, right? So absolute relativity, but the thing is relativity did not clash with our understanding of, I don't know, thermodynamics, for example. So that, and finally, these things need to make predictions that we can then test, right? And so there are some recent theories about modifying gravity, which suggests that there are these incredibly faint effects in certain other astronomical features, except when people have done the math to figure out how easy it would be to detect these other things, turns out we may not have the technology to do that for another 100 years. So, but it always is the case that if someone comes up with a theory, I am pretty agnostic about the type of things I want to, like, I don't care. If you tell me there's a modification of gravity, you have to tell me though what I have to look for to find that. And I'm happy to build an experiment to look for that. So we're not ignoring that. So can we go with the green and then we'll go with you? Oh, sorry.
Yeah.
Yes.
My question was, at one point you said either theoretically or you've got some reason to believe they're 10 to the 30th on this side,
Yeah.
and 10, so that's 10 to the 60th times difference, and that doesn't make sense to me because those numbers are so huge.
Yeah.
You're saying there's basically one thing that could be,
Yeah,
you're not sure
you
if
could
it's 10 to the 60th or 10 to the, that spread is so wide
Yes.
that it's
Which gives you maybe a sense of how maddening this job is, right? Because and the reason we can say that is because you could write down theory models that are completely consistent with all other known laws of physics that explain universe formation and explain things like the CMB and are consistent with all relativity and quantum mechanics and stuff like that for objects that maybe have closer to the size of a baseball than they are to a subatomic particle, and also potentially so tiny that their wavelength is the size of galaxies itself. Is not a satisfying answer to your question. I know it stretches the mind a little bit, but it's just we've kind of followed the math at
It just
times.
shows you where we are.
Where we
in
are,
the-
right?
in
Yeah, exactly.
the knowledge.
Yeah, I apologize, but I think you've had your hand up for a while, so we'll go to you and then we'll go back there. Yes, sir.
So the explanation of the galaxy's rotational speed.
Yeah.
Is that there's all this extra mass outside the center,
Including in the center, so it's just a halo that's everywhere.
Oh.
Yes,
diffuse.
diffuse, yes.
Okay, but gravity drove the creation of the stars and galaxies
Yes.
from primordial fluctuations.
Yes.
Gravity drives that stuff together.
Yeah.
And dark matter interacts with gravity. So
Yeah.
why is it still spread out so much? Why isn't it also sucked up into the center?
Yeah,
like
so-
regular matter.
right, so there are some some motion constraints, right? So it's kind of the same reason why, like, galaxies themselves are not clump-like points. They have some inherent velocity and spread in motion. So the same argument that gets you that galaxies are have extended shapes also gets you some of the ways explaining why these things are not just clump-like or completely clumps. That they have some inherent initial motion, and that they're able to form these elongated. So they're not necessarily completely spherical, they are elongated disks and blobs.
I had a similar questions.
Sure. Sorry, before we get to that, can we answer?
Actually, it's a little bit closer to his. If I move
Okay.
out radially from the
Yes.
center of a galaxy.
Yeah.
What does the distribution of dark matter look like? Is it uniform?
No, it does fall off similar to a galaxy. It doesn't fall off as dramatically, and there are some arguments that I'm not well versed in, but then there are some theory and computational reasons why that's the case. But it does have more density at the center. It's more dense at the center. Sorry. Can we go here?
Well, I was just going back to the
Yes.
question with the same questions. Maybe the dark matter is between the stars and not within the solar system, so.
Yeah, no, but then we think it's between the stars and it's in the solar
It's
system
in-
as well. So if we think about the WIMP paradigm, right? One way of getting a handle on how much dark matter there is on Earth right now is if you make a fist, you expect maybe about 50 dark matter particles in there at any given instant. If you make some assumptions about it being 100 times the mass of a proton. So there are certain areas where closer to the center of the galaxy it's more dense, but on Earth we think based on our position that's the sort of density we're expecting, which is why we hope that once in a while you get these interactions. Sorry, we'll go with you. The red, and then we'll go green, and then we'll go back.
Has dark matter had any effect on the expansion of the universe? And then the other question is, what about the old brainwave scenario where it's a parallel universe, we're seeing the effects of matter in a parallel universe?
Oh boy, I'm not qualified to answer that second question.
Okay,
Uh,
I've heard that theory.
Yeah. There are people who write down all these interesting theories, right? That like you can have parallel universe. I put my experimental hard hat on and I ask you, can you point to me a signature that I can go in my lab and try to measure, right? And then if you can, great, I'll go build an experiment that tries to do that.
Okay.
Yeah.
And then the idea of the effective rate of expansion of the universe as it slowed down dark matter.
Yeah, so dark matter then exerts a gravitational
Right.
thing which counteracts. By the way, you guys may have heard in popular science this other term called dark energy,
Right.
which we have not talked about at all, but it's a similar concept in the sense that it's a word covering our ignorance. We don't know what it is, and so we call it dark energy. It does some other weird stuff. So it does maybe counteract some of that. It's very model dependent, but you have to include it when we talk about those universe formation models. You don't get the answers you do unless you include some dark matter component.
So it had the effect of slowing the expansion somewhat.
Some, yes.
Okay.
We'll go with you, sir.
Yeah, if you ask an average non-scientist like me, and you
Yeah.
mention dark matter, if you come away with an idea that it's uniform, it's not after listening to your speech.
Yeah, it's not. It's not.
And that's for sure.
Yeah, so our best studies of like, we found places where we think there are no dark matter, like voids in the universe where it isn't. And if it was something that was just uniformly permeating everything, we wouldn't be able to see that. It does have structure, right? So which is why it makes us think that there are laws that guide this. And it's an incredibly exciting academic enterprise to try to find these laws.
The dark matter here isn't likely to be like dark matter over there.
We hope it is, right? We hope that, because then you have to introduce this complication that the stuff we see here is somehow, or like the stuff over there has somehow evolved in a different way than the stuff here. So we're hoping that all the dark matter is the same. We may find out later that it's not, in which opens up even more questions. I'm gonna go with the gentleman in the blue, then the red, and then you. So we'll start there.
Has the neutrino been ruled out?
Yes. So neutrinos, right, are these other subatomic particles which interact very weakly, but we have detected them. We know that they're produced in nuclear reactions like that happen in the sun. They're often called ghostly particles. They interact very infrequently, but we have pretty good understandings of them. And we don't think, people did have the idea that neutrinos could be dark matter. Didn't quite work out in some of the modeling and some of the experiments that tried looking for that. Sorry, yes, sir, in the red shirt.
So I've read where when in accelerators they try to accelerate particles.
Yes.
They get close to the speed of light.
Yeah.
And then they start gaining mass.
Uh-huh.
They can't keep directly changing it.
Yeah.
Target speed. Is there anything to that plays into this at all?
That effect of gaining mass is actually one of perspective. You can interpret it as gaining mass, or you can argue that it just takes more and more energy to accelerate these things to closer and closer to the speed of light. But to your point, that is exactly one avenue people try to look for dark matter, right? In those collider experiments, if you smash together all these protons and stuff like that that are going really fast, if you keep increasing the energy, the likelihood you may be able to create new and exotic things goes up. So you're always generally rewarded for making things go faster and faster and dumping more and more energy into smashing things, because you may discover something unknown that you're otherwise energetically infeasible for you to have detected previously when they were going slower. Okay, why don't we take 2 more questions and we'll try to wrap it up there. So we'll go with you, sir.
I was wondering if dark matter has angular momentum that has a role in shaping of the clouds of it.
Yeah, so it can, it does. So there might be some intrinsic angular momentum to the particles itself. We expect these things are spinning, so there is some extrinsic angular momentum to it as well. If you've heard of the concepts in subatomic physics of spin, some models say this dark matter, because it's a subatomic particle, could have some spin. And these all have macroscopic effects that might change its behavior. But again, it's kind of the Wild West. You can write down something which works, and then it's up to us. If it gives us a more unique signature to look for, great. And finally, we'll close it out with you, sir.
Why couldn't we balance the mass of the universe by assuming that there are super large stars that the light does not reach the escape velocity?
Yeah, so that you are in effect saying that's a black hole then, right? Because the light can't escape that object. But I think to in a similar answer to a question posed earlier, we have better and better tools of estimating the number of black holes out there. There was even this new experiment called LIGO, which can attempt to hear gravitational waves from colliding black holes. And every extrapolation we've made in counting these number of black holes that exist suggests that it is incredibly unlikely for it to make up the most of this missing mass. You can maybe account for 10% of the missing mass if you make some generous assumptions about the existence of these black holes. But we're at the point now where we think we have tools to be able to detect these black holes, and we just are not counting enough of them to make up that. I'm more than happy to take questions in person over here, but I think maybe we can wrap up the session. Thank you again. It was a wonderful opportunity.